Okay, dokie. Hello, I'm Sam. It is actually week 10 of the term, but I did not make a week 1 and 2 video, so I am doing that now. So anybody who's studying for the final and wants to review the basics of acids and bases, this will be hopefully some help to you. Possibly this could be help in future terms, not just the spring of 2023 here at Portland State University. So again, this is the basics, and I mean pun intended, pun noted, pun constantly occurring. This is the basics of bases and acids. I did that backwards just for the pun. Not that bases come first or last, but let's just dive into this. There's a bunch of questions here, but it should go pretty quickly, I think. So first thing, there are multiple definitions of acids and bases. The one that we're talking about right now is Bronsted-Lowry, where essentially a base accepts the proton, H plus. That's a proton. It's just a nucleus that's a single proton, no electrons. And an acid donates the proton. So, show by suitable net ionic equations that each of the following species can act as a base, meaning that it's going to accept a proton. So H2O plus a proton, which it would be appropriate to call that aqueous, that's liquid at the moment, is going to become, it already had two H's, now it has three, H3O. But that proton did not bring an electron with it, so it does have a charge. And now it has become hydronium. And so again, the species that acted as a base, the water is the species that acted as a base because it accepted a proton. And when it did that, it became its conjugate, acid hydronium. So OH minus plus a proton, oops, that was a hydrogen. I meant to say that was a diatomic hydrogen molecule. Hydroxide, which would be aqueous, I'm sure, plus a proton, which will also be aqueous, is just going to lead to good old-fashioned water. Nice. Okay, so that's A and B. So really what we're doing for all of these are Bronsted-Lowry base. To some extent, we're just plopping a proton onto each one of these, and in doing so, we are raising the charge. So I just want to note that for H2O, the charge initially was 0, and then for H3O, it went up to +1. For hydroxide, the initial charge is -1. We added on a proton, and then the charge went to 0. It became neutral. So here we are with neutral ammonia. There we go. We're going to add a proton, and now we're going to have ammonium, which has a charge. Here we have cyanide. Let's pop on a proton. Cyanide has a -1 charge, and now we will have cyanic acid. I want to say that's called cyanic acid. I might be off on that. Maybe I'll Google that, because I would like to know. Let's just confirm. Hydrogen cyanide. So it's not called cyanic acid. I made that up. And I also just dropped my pen. And it's not just any pen, it's the writing tablet pen. But it definitely couldn't have gone. Oh, there it is. Okay. Whoop. Pen obtained. Sorry about that. Okay, so this is just called hydrogen cyanide, not cyanic acid. I made that up. So let's note here that this sulfide has a 2 minus. So when we add a proton to it, the charge will go up in a positive direction by 1, but it will, so now it's hydrogen sulfide. It still has a -1 charge. Let's look at this last one. Let's note that this phosphor or dihydrogen phosphate, there might be another name for it, but that's what I'm going to call it, has a -1 charge. So this makes it phosphoric acid right here when we put that proton on. Now, not all of these would be favorable reactions, but this question asked us to just identify how all of these given species could act as a base, and what that means is they're, in the Bronsted-Lowry sense, what that means is they're accepting a proton, and therefore their charge is going up, and they have one more H in the product than they had in the reactant. So again, the base accepts a proton, the acid donates. The thing that accepts a proton and gains a proton becomes the conjugate acid of the base. The thing that loses the proton is the bronzolaric acid, and once it loses it, it becomes the conjugate base. And I think I might have just said conjugate base here when I meant acid. Sorry, I watch these videos back and I accidentally say the opposite of what I mean far too frequently. So trying to be on the ball with that. But the Bronsted base gains a proton and becomes the conjugate acid. The Bronsted-Lowry acid loses a proton and becomes the conjugate base. So let's go through, and what I'll do, I'll highlight these. So we're going to say that we'll do the acid in green first. So one thing to note is that the Bronsted-Lowry acid and base are going to be on the reaction side every time. They're going to be on the reaction side every time, and the conjugates are going to be on the product side. So let's go through and just look at all these reactant sides first and see who's giving and who's losing a proton. So it looks like here, this is what's giving the proton. It looks like here, this is what's giving the proton. It looks like, well, it's obviously not chloride right here, right? Let me zoom in on that. It's obviously not chloride. Chloride has no protons to give. And I guess in this previous one, it's obviously not cyanide. Doesn't even have a proton to give. That's clearly giving the proton. Looks like here, sometimes we do have to look over on the other side to really know, but it looks like here, this sulfate is a product, so that lost a proton. Looks like here, obviously that lost a proton because the oxide didn't have one to begin with. Ooh, this is a little more complex looking, but let's see. What do we have? Who's got more hydrogens than they had before is what we're thinking here. So we had 6 waters and a hydroxide. Now we have 8 waters. Sorry, when I said 6 waters, I meant to say, no, that's correct, sorry. No, it's not. We have 3 waters. I should have said we have 3 protons in the water. And here's a 4th one. So that's 4 total protons. And over here, I'm sorry, that's 6 plus 1, that's 7. And over here, I see that there's 8 protons on this copper, right? So that sort of suggests that the aluminum complex ion over here, this aluminum heptahydrate or aluminum hexahydrate, and I could get in there and figure out what oxidation state of aluminum it is, but I'm not going to do that for the moment. Let's just see if this is correct. We have 10 protons over here. Oh, maybe can I move my face around? I can't. I just noticed that the way I have this, my face is over what I'm writing, so let's just move that there. Okay, so we have uh, 12 protons here. Here we have 6 and 1 more, so here we have 7 protons. Then over here we have 2, or that's 8 protons. And here we have, there's 10, 11. Okay, so there you go. The aluminum is what lost a proton. It donated it. That makes it the acid. And in this, so that was the hardest one here by far. But it just really involved, paying attention to those numbers and adding them up correctly. And I do say correctly because I started to add them up incorrectly several times. So pay attention to that. It looks like this loses a proton there. So the conjugate base, I'll do in dark green. So the light green, the acid becomes its conjugate base on the product side. Started as water, became hydroxide. Up here, it started out as nitrous acid, became a nitrate. I think that has a minus. It should have a minus. If it doesn't, that's a typo. Well, okay. Let's continue. Here we had sulfuric acid. It became. Oh, I guess the minus is there. It's just my highlighter gets rid of it because it's so faint. So put it back. That became that. That became Well, this one's an interesting one actually to think about. Hmm. So that acts as an acid. So definitely this is its conjugate base. But that makes me think, okay, so is there a conjugate acid then? Huh. Yeah, it's also the conjugate acid. That's an interesting one right there. We're going to get to that in a sec. So aluminum hexahydrate over here is our bronzed-Lowry acid that results in this conjugate base. And hydrogen sulfide, dihydrogen sulfide, is the acid that results in that base. And then the rest of this just kind of fills itself out. So let's go ahead and assign the base this nice rose color here. And we could overthink it, but to underthink it, it's just whatever else is on the reaction side. If we're going to overthink it, of course, it's the thing, once again, that's accepting the proton. And you can't have one without the other. Even if the proton itself maybe just was around, then I guess you could say that the proton itself maybe is the acid. But there's always both sides of this yin-yang scenario going on here. And so once the pink thing, once the Bronsted-Lowry base accepts a proton, it becomes the conjugate acid. Well, now these tend to go back and forth, but we're just now, and again here, once the oxide, this O2 minus, accepts a proton, then it becomes OH. So you could say that basically this same OH product is both the conjugate acid and conjugate base. I hope that's not incorrect. It seems right to me at the time. So there you go. That's how those all work. And again, this is actually quite simple at this level. Whatever donates a proton is the acid. Whatever accepts the proton is the base. That is the Bronsted-Lowry definition of acids and bases. Okay, so let's really talk about what this means. The ionization constant for water. You have water, and to some extent, and this is reversible, you know, that water and another of itself. So let's say we had two waters. I should say, yeah, so two waters. One of those waters is going to give a proton to the other. So the one that gets a proton becomes H3O plus. And the one that lost the proton becomes OH minus. This is a liquid. Water is a liquid at standard conditions, which is essentially what we tend to be talking about. I guess here we're talking not standard, we're talking 60 degrees Celsius. So not quite standard, but it's still a liquid is the point. We know it's a liquid because water is a liquid between 0 and 100 degrees Celsius. Those are both aqueous. A K expression of any sort is always products, and in this case I'm doing it as concentrations, over reactants. Now, Kw specifically, therefore, is our products, which is H3O plus. And remember, in these expressions, we exclude solids and liquids. And the reason for that is that if we put water down here, which we can, its activity, which is sort of a nuanced term, but activity means how much a substance behaves like itself. Um, because dissolved aqueous hydronium or dissolved aqueous hydroxide behaves differently than if you had somehow a pure like cup of hydronium or hydroxide. I don't know if that is a reasonable thing to even talk about. Probably be some weird plasma or something. But it has an activity. So aqueous and gas go into these expressions, but liquid and solid don't. Since that's liquid, it's as if that equals 1. So basically this whole thing equals 1. So the Kw is the concentration of hydroxide and hydronium. And it looks like for literally every time that we get one of these, we get one of these. There is no case in which, if water is the only thing that's going on, there's no case in which we're going to generate a hydronium and not also generate a hydroxide. So the concentration of hydronium and hydroxide should equal each other at any given moment, because otherwise you have just a bunch of water. And we do have a bunch of water. That's the thing. Look at this KW. So this is what this whole KW thing means here. Move this stuff around and clean it up later. So the KW is going to equal, and let's call these X, by the way. Whatever it is, it's X, and it equals itself. So it equals X times X, right? X times X. And that equals 9.311 times 10 to the minus 14th, right? We're talking 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, and then there's our 14. So that's what KW equals. That's a very small number. And that makes sense. Mostly the water stays water. It mostly does not become acid and base. This probably explains why, if you were to drink water in the near future, which all of us should, that water is mostly not acid and mostly not base. So it mostly doesn't like dissolve your guts. Sorry to get a little bit macabre there. But in this case, we are seeing water that I believe is ionizing slightly more, but just slightly more. Since it's hotter, it's ionizing slightly more than at room temperature. At room temperature, this would be 1 times 10 to the minus 14th. So by heating it up, it's ionizing more. So the KW equals 9.311 times 10 to the minus 14th. And that equals x squared, right? That equals those times each other. So the square root of 9.311 times 10 to the minus 14th, which, let's TI-80 for it, or whatever your preferred calculator method is, including doing it in your head. Ooh, my TI-84 is almost out of batteries right now. So let's see if it can make it through this video. If not, I'll just use Desmos or something. So the square root of that, which, could we have done this in our head? Actually, now that I just got the answer, I'm like, actually, maybe. We're close. But that's what it is. So that is going to equal the concentration of both. That's that. So that's that part of the answer. And then P of anything, P, OH, and pH, P just equals negative log base 10 of whatever. So what does that mean, by the way? I think this is a really important thing to keep in mind. When it comes to something like KW here, we've got all these zeros. Each one of these would give us another 10. So if you had like 10 to the negative 1, that moves your decimal place from here to here. 10 to the negative 2 moves it here. 10 to the negative 3 moves it here. To the negative 4, to the negative 5. So this is 10 to the negative 14 right here. The P value tells you how far below 0 you are. Or really, how far below 1 you are. So it makes sense. We're at the super tiny number. We should expect the negative log of this. It's not that tiny compared to that, I guess. But we're going to expect it to be about, I'm guessing, like 8.2. Let's find out. So negative log of this number you just told me. Okay, I was wrong. About the 8 thing, it turns out that it is, oh, so therefore pH is going to equal the negative log of base 10, which your calculator is going to ultimately do base 10 unless you tell it otherwise, which is going to equal 6.5. And since our concentration of hydronium and hydroxide are the same, that's going to equal the pH and the pOH. Okay, so that's all it asks. So this means that, again, here we go. This is the constant. Oh, that was a bad way to do that. Circle it with orange. So that is the, oh, and units. When you do the log, it gets rid of the units. pH and pOH don't have units, but concentrations do. Molar. Moles per liter, right? Okay, cool. So let's deconstruct that. Oh, I see. I need to move these around. As usual, I did not really predict how much space I would take. So let's bust these out really quick. And while I'm busting them out, I feel like I must have a calculator charger like within very close reach. But that's cool. What I'm going to do is just turn the screen off until I need it again, which is going to be any sec. I guess I'll just open Desmos. Desmos, one of many online calculators. I like it in part because it leaves a trail of all the calculations I just did. So calculate the pH and pOH of each of the following substances which ionize completely. So this is important because water and many other things do not ionize completely. But by the way, we have a strong acid, which I had previously denoted acids in green. So let me just keep up with that. So we have a strong acid, another strong acid. Here we have strong base and another strong base. So these dissociate completely. So when HCl goes into solution, it becomes H plus and Cl minus. And that's our reaction. In our initial HCl, they're telling us that we have 2 molar. And our initial concentration of hydronium and chloride are 0. And we are told that it completely dissociates. This ice table is actually kind of silly. So our change is all of it. Our equilibrium concentrations are therefore like that. So we can actually kind of stop here because what they're asking us is for the pH and pOH of each of these. And by the way, we're now at that. So our Kw at 25 degrees standard equals 1 times 10 to the minus 14th. The previous problem, we were at 60 degrees, right? So that means Kw is Ka times Kb, and Ka and Kb equal each other. So that means if we find one or the other, we can convert from there. So that probably bears more discussion, but I'm going to proceed and just calculate this at the moment. So the pH of this first one is just the negative log of 0.2. So I'm going to do this up in Desmos. The negative log of 0.2. This super makes sense. So let's go with this blue. So the negative log of 0.2 equals 0.69. It's very close to 1, right? It's strongly acidic. And at any given time, the pH equals 14 minus the pOH. Yeah, I said that right. Which is related to this. It's like because the PW is 14, which equals pH plus pOH, which is because of logarithm rules. When you divide logs, when you take logs of things that are multiplied, it's like they're added. That's what's going on there. Okay, so if our pH is that, then the pOH is 14 minus that, which is going to be 13.71 approximately. Did in my head. All right, let's actually just have Desmos confirm that though. So 14 minus that is that. Yeah, 13.3. So good thing I checked. I messed up. I should just use a calculator the whole time. Okay, so that's the first one. Um, let's go ahead and do this one next because the other acid one. It's going to be the exact same thing. So the negative log, because it fully dissociates. So just replace this with HNO3 now. And let's replace this with NO3 minus. Otherwise, oh, and let's replace this with 3, 3, 3, 3, 3, 3. No more twos. Sorry, that's a terrible mess, but you see the point. When it's strong acids and bases, it truly is this simple. Now that is a very high concentration, so this is going to be possibly a positive. I still don't think it's going to be positive, but it's going to be a very strong concentration. Let's find out. Negative log of 3. Oh, there we go. We have a negative pH. When I said positive, I meant negative, so sorry about that. So the negative log of 3 is negative 0.477. So that's the pH. So this is super acidic, and 14 minus that is going to be plus that. 14 minus a negative is plus, was the POH. Very not basic, very acidic. So that is hydrochloric acid there, and our nitric acid. And for our two bases, we're going to do the exact same thing, just the opposite direction. Ooh, but this one has a caveat. So let's start with NaOH. Once again, NaOH, sodium hydroxide, you put into solution, becomes that, and that. This is the one we're interested in, the hydroxide part. Since it fully dissociates, we start with that much of that, and it basically ends up that much of each of these. So the negative log of that the negative log of 0.0031. See here. So the negative log of 0.0031, 2.509 basically, which is the POH, and so that means the pH is the difference from 14 uh, minus that. I think I used the wrong preposition in that sentence, but that's okay. So in this case, we are looking at 11 point, basically 0.49, right? Yeah, cool. Equals the pH. So note, this is basic, so the pH is very high. POH is low, pH is high. Now this is an interesting one because our calcium hydroxide, calcium 2 hydroxide, becomes a single calcium 2 plus ion and then 2 hydroxides. So we start out, oh, oops, I used the calcium hydroxide number for this one. Sorry, let me fix that. My bad. On, there we go. Okay, my bad. On this one, I meant to say 0.0143 because I'm doing sodium hydroxide here. So 0.0143, and so that POH is actually 1.84 and 12.15. Okay, so sorry, so that's this right here. Now with the calcium hydroxide, we start out with that, and we lose all of that. Ending up with 0 of our calcium hydroxide. And as far as the calciums go, we start out with 0, but then we add that much, so we end up with that much. However, for every 1 calcium hydroxide, 2 hydroxide ions are yielded. So here we have plus 2 times that. which is, of course, 6.0062 molar. Molar. So what that means is to get the, and this is OH right here, right? So our POH is going to be the negative log of that. Again, this is all about that full dissociation. And so our POH is 2.207, which means that our pH is 14 minus that, which will be 11.793. Pretty sure I nailed that. Let's find out. Oh, yeah. Okay, cool. So that is that problem. Let's look at the next one. What are hydronium and hydroxide ion concentrations in a solution whose pH is as given? So since P equals negative log base 10, to undo a P, you do 10 to the negative. That's how you undo it. So if our pH equals 6.52, our concentration of H, by which we mean H plus, equals 10 to the negative 6.52. That's how you undo a P. And that, oh man, I don't know if my nose sniffles show up on camera, but I just almost sneezed, then totally caught it. Okay, so for this, our concentration of hydronium ions is 3.01995. I did too many sig figs there, but I'm just rolling with it. Times 10 to the minus 7th equals, well, it equals that. And there's several paths to figure out the hydroxide concentration. What I'm going to do is say that our POH equals 14 minus our pH, which equals 14 minus 6.52, which equals, oh wait, we got this. It's going to be 7.48. Yeah, 7.48 equals our POH. I guess I'm going to double check myself. 14 minus 6.52. Okay, we good. So that means that our OH concentration is 10 to the negative 7.48. And that equals 3.31, etc., times 10 to the minus 8 molar. So there you go. Our hydronium concentration is that, and our hydroxide concentration is that. And let's note that our hydronium, right here, to the negative 7th, our hydroxide to the negative 8th. So this is fundamentally an acidic solution, which makes sense because that is lower than 7. All right, not too bad, number 21. Thank you for being not too bad of a question. And this is officially 2 weeks worth of stuff, but hopefully it's all straightforward enough that I can fit it in real quick. Let's see how long we're at. 34 minutes. How are we doing? How are we doing? All right, I should expedite it. Let's expedite this. So, explain why the neutralization of a strong base and a strong acid and weak base gives a weakly acidic solution. So the basic idea is this: if you have a strong acid, let's call it H strong, and you have some sort of base, let's call it base minus. So the neutralization is that when H strong goes into a solution, it becomes H plus and strong minus. But strong minus is very bad. It's a very bad base. It doesn't like getting a proton back. H strong, our strong acid, loves getting rid of a proton, so its conjugate base does not like getting one back. Whereas base minus, this weak base, it's pretty good at picking up a proton. So this proton's going to end up joining onto base minus right there. So really what we're going to get, to some back and forth extent, is that we're going to have strong minus and H base. So from there, the reason that we're going to get a weakly acidic solution is because strong minus is a bad base, but this weak base is somewhat of an acid, meaning that now H base can go ahead and give that proton away too, to some extent, reversible to some extent. So since it's doing that to some extent, we end up with a weakly acidic solution. What this means ultimately is the solution is not going to have hydroxides around very much, because anytime there would be a hydroxide, H base is going to give it a proton, and it's going to become water. So we're not going to have hydroxides around, but we will have some hydronium around, because H base is around to give a proton to water. And depending on how much strong acid we use, we might just have an excess of that. But neutralization implies that it's the same quantity. It's the same number of moles. Same number of moles of strong acid, and this is what neutralization means. Number of moles of base. And that, of course, pertains to titrations and stuff. So that's the deal with that one. Let's keep rocking and rolling here. So the odor of vinegar is due to the presence of acetic acid, a weak acid. List all in descending concentration, all the ionic and molecular species present in a 1 molar aqueous solution of this acid. Okay, so we've got acetic acid. I'm going to call it H-acet. And see, it has that H right there it could lose. When it does, it's going to become acetate. It's going to become CH3CO2 minus. Okay, so acetic acid, it's aqueous, and the thing is, it is not a strong acid, so it's only going to partially dissociate. So when it does, we're going to get some H plus, which is going to immediately tack onto a water, making H3O plus. And then we're going to have some acetate, acid minus, right? We're going to have some acetate, and to whatever extent that this water has OH minus in it, this H3O plus is going to neutralize that. So I don't expect we're going to have a lot of OH minus, but at any given moment, you might have a tiny amount. The thing is, it says molecular species. It's an aqueous solution, so definitely water in standard conditions is 55 molar, equals the concentration of liquid water. So that's definitely the highest concentration. It says order of descending concentration. So the highest concentration for sure here is liquid water. The next highest concentration is most of this acetic acid, this weak base, most of it will not dissociate. So the second highest is going to be undissociated acetic acid. Then we will have, the thing is, every one acetic acid becomes one hydronium and one acetate, but water already has some hydronium. So we're going to have slightly more hydronium than acetate because water already brought some. Whereas the only source of acetate is whatever acetic acid dissociates. And again, since this is a weak acid, more of it will not dissociate than will dissociate. Actually, I don't know if that's always the case, but it is the case here. And then we're going to have, to whatever extent we might have some hydroxide, it's going to be trace amounts. because it's going to get basically instantly neutralized anytime it encounters an acetic acid. All right, cool. And they noticed 1 molar because had they said that it's 100 molar in acetic acid, then I guess that would be more than the water. Water's 55.5 molar. Good little tidbit to remember. Okay, let's keep charging on. Gastric juice, the digestive fluid produced in the stomach, contains hydrochloric acid, milk of magnesia, magnesium 2 hydroxide in an aqueous medium is sometimes used to neutralize excess stomach acid. Write the balanced equation and identify the stuff. So the balanced equation is we have HCl, your stomach acid. It's going to be aqueous. And we're adding it with magnesium hydroxide. Now the thing is, if this is balanced, then we have to account for 2 of these because there's 2 hydroxides there, right? So behind the scenes, here's a hydroxide and here's a hydroxide, and we need an H plus and an H plus, and those had their Cl minuses that just go over there. And this can become a water, and this can become a water. So we had 2 of those. So we have 2 waters, and then we also had 2 HCl's, or sorry, 2 chlorides. Now the thing is, if this were to be written as a salt, what we could do is combine this magnesium 2 plus with these 2 Cl minuses. In solution, I think this is more accurate. In solution, they're floating around as aqueous ions. But if you dried your solution and made the water evaporate, maybe what you would actually get is MgCl2 plus 2H2O. So, and I'm going to call it aqueous. So that's up to you if you want to write it as dissolved ions or as this salt compound. So the conjugate acid and base pairs, the conjugate base is the Cl minus, right there. The conjugate base, HCl was the acid, so that's our conjugate base. And OH minus was the base, so our conjugate acid is the water. The water is the conjugate acid of the base. And the magnesium is the counterion of. So would we call magnesium? Yeah, I guess really what we should do to be super thorough, let's call magnesium chloride is the conjugate base, or conjugate acid, because that takes care of both parts. Conjugate acid and base. Oh, sorry, conjugate base. That's the conjugate base. That's what happened when the chlorine gave up its protons. And the magnesium was receptive to gaining. Scratch that last sentence that I didn't finish. That was going to be wrong, but otherwise is all correct. Okay, let's keep moving. And we're getting close. What is the stronger base? That would be, what would we call that? We got a nitrogen with methyl, methyl, methyl. Probably got its lone pair on it. So that's CH3, 3, and trimethylamine. I'm going to call that trimethylamine. And we also have H2 borate. That's crazy. So which one of these is a stronger base? Meaning which one of them wants to accept proton more? Who wants to accept a proton more? Now, you could see that this methylamine, it could theoretically fit a proton right there and become like that, but then it would have a plus charge. the nitrogen would now be sharing one of its lone pair electrons with that proton that came in, which would give it a plus charge. However, on the other hand, there's a lone pair here that's represented by that minus. And if a proton comes along here and that lone pair and that proton get together, now we went from having a minus charge to no charge. So I think that this is going to be the stronger base, because if this acts as a base, then you end up with CH3, 3, and plus. You end up generating a charge, and that's bad. I mean, that's not stable, I should say. Whereas here, we started with a charge and we got rid of it, no charge there. So that became more stable. If it's going to become more stable, it wants that proton more, because these two starting material molecules are thinking like, hey, if I get a proton, what's that going to mean for me? If it means they're going to get more stable, they want to do that. If it means they're going to get less stable, they might not want to do that. Is it appropriate to personify uh, molecules and ions and atoms? Yes, it's totally appropriate to do it. Is it accurate? Probably not. But is it functional and sort of, in my opinion, crucial to our model of physics and chemistry? I think so. It's helpful anyway. Okay, so we're going to follow that same principle. So with this one, to start, by the way, we're talking the left side of the periodic table, right? The left side, right? Something like that, periodic table. Come down here, we have fluorine, and then chlorine, and then iodine, and then bromine. Except for I did bromine and iodine backwards. That's the important part. Chlorine, bromine, and iodine. In their native form, they all have 7 valence electrons, and they all would essentially love to steal an electron from a hydrogen. That electron ends up on the chlorine, and this becomes a proton, hence making them acids. So which one's going to be the best? Here's what you need to think about. Is there sizes or something like that? That's a chlorine atom, that's a bromine atom, that's an iodine atom, which means that once they generate a negative charge of -1, who does that negative charge influence more? Amongst chlorine, bromine, and iodine, well, once they have that negative charge, by the way, it's a chloride, a bromide, and an iodide, the big one can stabilize that charge. Like, I don't know, it's been a while since I've played any video games, but you can imagine like certain like monsters or something in a video game. If you do like 1 point of damage, that's it. They only have 1 hit point and they're gone. But then other monsters, bigger monsters, maybe take 10 or 100 hit points. So that 1 hit point, which is what we're talking about, is 1 minus charge, doesn't really make a big difference to iodine. One way that that is explained is due to its size. It's highly polarizable, and it can distribute that excess negative charge much better than chlorine can. So it's more stable, which means it's more happy to get rid of its proton. So in this case, the biggest one is the most acidic because its conjugate base is the most stable. They're all strong acids, by the way. All 3 of them are definitely happy to get rid of that proton, but hydroiodic acid is even happier than hydrobromic or hydrochloric acid. So same deal with the basicity. The whole concept here is most stable product wins. If the most stable product is going to drive these things to behave in the way we're talking about. So let's look at this. First off, water is clearly going to be the least basic. The least basic because water would prefer to just stay water. It has no charge, it's totally balanced, it's good to go. Now, chloride is the conjugate base of a strong acid. If it were to gain a proton, it would give it right back. So actually, now that I think about it, chloride is even worse than water. Water can take a proton. Chloride really hates it. So chloride is actually an even worse base than water. Now, between hydroxide and hydride, which remember, hydride is a hydrogen nucleus with 2 electrons, whereas a proton is a hydrogen nucleus with 0 electrons. So if it has 2 electrons, it would love to gain a proton, because if you have a hydride, if we add these together, a hydride and proton, you get H2. Very stable. Nature loves it. So I'm going to say that the hydride is probably the most basic, even more so than hydronium, because hydronium is somewhat stabilized. Hydride is think about the difference an oxygen and a hydrogen versus just a hydrogen. It's the same deal over here. This hydrogen cannot handle that lone pair. This oxygen is fine with these lone pairs. So that's what I'm going to put for B. Okay, let's keep raging through these. And, well, actually, I'm going to leave most stable product wins, because that's a crucial part of this. Okay, so for basicity, let's see. Oh, that could be hydro. So that is a strong acid. That's I want to say that's hypochloric acid. Hypochlorous. That's hypochlorous acid, which is a fairly strong acid. Here we have silicon tetrahydroxide and magnesium hydroxide. So magnesium hydroxide is a strong base, I'm pretty sure. Silicon, that's got to be pretty balanced. So this one I'm actually like not super sure on, but since this is a pretty good acid, it must be a terrible base. So I think these are actually in order. Magnesium hydroxide is more than happy to dissociate into that and then let its OH groups pick up protons, right? So I'm going to say it's magnesium hydroxide. I'm going to say it's the order that it is. Let's see here. Is more basic than. I might be wrong for some reason I'm not thinking of on this one. That's my thinking. This hint tells us we happen to know that that is a good acid. So it's going to be a bad base. If it's a good acid, it's not a good base. That's how this works. Okay, so this last one. So this is interesting because that's a pretty decent acid. Hydrofluoric acid, HF, great at being an acid. Methane is a terrible acid. Ammonia is a terrible acid. Water is a mediocre acid at best. So this one I don't even really have to think about that much. Definitely HF is going to get rid of that proton just because that's the next one up here, right? It would love to get rid of that proton. Water is going to be the second best. Now the question is, who's acidity? Who's more likely to get rid of a proton? Nitrogen or carbon? I'm going with nitrogen on this one because if that nitrogen lost a proton, it would become an amide ion. If this carbon lost a proton, it would become CH3 minus a carbanion, a methyl, a methide, a methanide, a methyl car. That's super unstable. Nature wants to get rid of that as soon as possible. Whereas this could last for a while. It'd still be a very strong base, but it could last for a while. So that's what I'm going with. So that one was already in order as well. I think. If I'm wrong, I apologize for misleading you, but if you know I'm wrong, then like leave a comment explaining why. And it will be checked out. Okay, let's keep ripping through these. Which of the following will increase the percent of ammonia that is converted to the ammonium ion? So that's when ammonia acts as a base, it gains a proton, and it becomes NH4 plus. So if we add sodium hydroxide to the water, the hydroxide is going to soak up those. So that's actually, right, the hydroxide is going to grab that proton instead, so you'll get less ammonia. So this will decrease, so it's not A. Now if we add more HCl, then we're going to have a bunch more protons floating around, which means we could totally get that. So this one's going to increase it. If we have a bunch of NH4 already, then that will not actually expedite this because of Le Chatelier's principle. It'll basically make this NH3 be like, I could become NH4, but there's already so much of it, so I'm not going to. So that's going to decrease it as well. So in this case, adding acid is what will allow ammonia to act as a base. All right, we just got a few more. My phone's blowing up. Let's see if anything cool. All right. Calculate the concentration of all these species. I think I was only supposed to do certain ones of these, so let me see here. Okay, so we're going to ignore the ionization of water for these, so we're just looking at it based on what it says here. So I think we should do this one. Maybe let's just do this one, because like I need to know its K values, yo, of all solute species in each of the following, and show that. See, I feel like we need the Ka value for all these because Ka, after stuff dissociates and we're at equilibrium, is going to be our hydronium concentration times our conjugate base, so A minus, conjugate base concentration, over our initial acid concentration, HA, not a minus. So I am actually unclear how I would answer these without looking these up. The thing is, I could go look them up in a table. And if I recall, that table is called Appendix H of the textbook. I think it is. Let me find out for sure. We've got our Chem Libre texts, and I am looking in the appendices of the Gen Chem 2E texts, and I am looking at ionization constants of weak acids, which indeed is referred to as Appendix H. Okay, so let's see if they even have all these. So hypochlorous. Yeah, hypochlorous. So we do have it. So this is the thing. You'd have to go to answer any of these. So it must be that for this one, that must not be in Appendix H. So Appendix H of the textbook, or wherever on the internet, has the KAs for all these. So I'm going to just do this first one, and then I'll leave it up to you to do the rest if you want. So I look in Appendix H, and the Ka of this hypochlorous acid is 2.9 times 10 to the minus 8. So that equals our concentration of hydronium times our ClO minus, which is our conjugate base, over whatever amount of hypochlorous acid does not dissociate, right? And for our rice table, it's probably an X is small scenario. Definitely is. So however much this loses is going to basically be nothing compared to how much isn't lost. Uh, and we kind of know that because if we divide the, oops, sorry, that's the wrong one. If we divide the concentration by the Ka and it's over 400, then X is small, which basically means that we can just put the initial concentration of that down here. So the rice table here, we have our HClO comes H3O plus. Now, obviously, I'm sort of implying the part where water is an intermediate there, but that's what happens. Our initial is 2.9 minus 8. Our initial, those are 0. This loses X, this gains X, this gains X. But again, we're saying X is small, so 2.9 times 10 to the minus 6 minus X, what we're saying is that that is essentially equal to 2.9 times 10 to the minus 6. However, X is not so small that we ignore it for multiplication. So X and X, which means that 2.9 times 10 to the minus 8, when I said 6, I meant 8 over here, Oh, wait. That's the Ka. I messed that up. That's the Ka, not the concentration. The concentration is this 0.009. Sorry about that. 92 minus x 0.0092. So 0.0092 minus x is basically the same thing as 0.0092. So our Ka now equals x times x over 0.0092 molar, whatever it's worth. The units kind of end up going away when we do this. So that means our Ka times our concentration of our weak acid equals x squared, meaning that x, the concentration of hydronium, is going to be the square root of the Ka times the concentration of Ha. And that means that x is going to equal the square root of 2.9 times 10 to the minus 8th times 0.0092. And let's Desmos that. So 2.9 times 10 to the minus 8th. That whole thing times 0.0092. That's that. And then the square root of that equals that. So 1.6 times 10 to the minus 1, 2, 3, 4, 5 equals the concentration of hydronium. What were they? They're probably asking for the pH, so now we probably just have to negative log that. Calculate the concentration of all species. There we go. So that's the concentration of hydronium. That's also the concentration of our chlorate, our uh, conjugate base. There we go. Sorry, that took me too long. And again, we're saying that fundamentally this didn't change. Now, if we did subtract, we could say that that lost it, but that's saying this. Say it lost that 1.6 times 10 to the minus fifth. So that equals, this one I guess is cutting it closer than some, but really not. 194. So this is essentially the same thing as what we started with. Let me super confirm. Now, this means that if we had a bigger concentration, yeah, that's definitely works. So if we had a bigger concentration, then we couldn't have done that approximation, the x is small approximation, but we didn't, and so we did. Okay, so you would just look these up. There's Appendix H for the acids, Ka. There's Appendix I for the bases, for your Kbs. And when it's Kb, it's all exactly the same except for you end up with OH minus and a conjugate acid over your starting base. So I'm going to leave you to do those because we are at an hour here, and I'm just going to take a look at these last two. So there's some more. You can do that kind of problem if you want. I'll pull up on it, and you could pause it and try them. And if you desperately want to know if you did it right, reach out, and we'll let you know. Okay. So we have this one, and okay, and one more. Let's actually do this one first, and we'll circle back to this last mathy one here. Okay, so determine whether aqueous solutions of the following salts are acidic, basic, or neutral. So when this dissociates, looks like what we're going to get some aluminum 3 plus plus 3 nitrates. Now these nitrates are the conjugate base of a strong acid, so they're not going to act like bases. The aluminum, however, could act like an acid. In the Lewis sense. The aluminum could be an electron acceptor. If it accepted electrons, that would lead to there being protons in the solution. So I'm going to call this acidic because the aluminum can act as a Lewis acid, which means the Lewis definition is just like the Bronsted, except for we're talking about electrons. Lewis acid accepts. So that Al3 plus, if something came by with electrons, there could totally be a bond that would form. And so the solution will be kind of acidic. How about for this rubidium iodide? I don't know much about rubidium. Iodide, conjugate base of a strong acid, so that's not going to act like a base. Man, I don't even know where rubidium is off the top of my head on the periodic table. Let me look. Rubidium. Oh, rubidium's an alkali earth metal. I probably should have known that. It's just below potassium and sodium. So rubidium also is fine. It does not want to get involved. We're calling this neutral. Basically, rubidium is totally cool giving its electron to iodide. Neither of those. Rubidium does not want to do anything. Iodide does not want to do anything, so that's neutral. Here we have that's going to dissociate into potassium, which is the conjugate acid of the strong base, so that's going to be neutral. And then we have HCO2 minus. That's called bicarbonate. No, bicarbonate would have another O, would be HCO3 minus. So what is this called? Hydrogen carboxylate, maybe? Probably hydrogen carboxylate. Whatever it is, it clearly would love to gain another proton. So this is basic. That clearly wants to gain protons so that it can become H2CO2 without a charge. Okay, so here's our last one. Bromide will take a electron and get out of there, and it is the conjugate base of a strong acid, so it's not trying to react. And then we'll have CH3, NH3 plus. Um, that's methylamine and methylammonium. I think that that would actually love to get rid of a proton so that it could become CH3NH2 without a charge, methylamine. So in that case, I'm going to say that this is an acidic one because it would love to get rid of a proton. So the big maxim that I employed there was the conjugate base of a strong acid is non-reactive, essentially. The conjugate acid of a strong base is non-reactive. That's what makes the other thing strong. Okay, great. Let's do this one last one. And this was 2 weeks worth in 1 hour, so that's pretty cool. Of course, it's pretty simple stuff on an acid-base sense. But until you've done a bunch of these problems, it doesn't seem simple. So if you don't feel like this stuff's simple, I totally get you. I did not used to think it was simple, even though I just said that. Okay, so that molar. So first off, let's test for x is small. X is small. Let's test. So our concentration of HA is that. Our Ka is 1.34. I'm pretty much thinking x is going to be small, but let's just super verify it. So 0.698 divided by 1.34 times 10 to the minus fifth. Oh yeah, way over 400. So x is small, so we're going to roll with that. So based on having already done the rice table for the previous one, I'm just going to set it up like this. X equals the concentration of protons, and it's going to equal the square root. This is just like the previous problem, since x is small. It's going to equal the square root of the Ka times the starting concentration. So the Ka, 1.34 times 10 to the minus fifth, times 0.698, and that is momentito. Let's see here. that equals the square root of 0.12319, something like that. 5, which equals 3.058 times 10 to the minus third equals our concentration of hydronium. So to find the pH, all we have to do is the negative log of that. So the negative log of that equals the pH, which equals 2.5145. So that equals pretty acidic. Does this make sense? Yeah, that makes sense. It's called an acid. It's propionic acid. IUPAC would be propanoic acid, but same deal. 3 carbons you see, and a bunch of hydrogens, including one that you can get rid of. So it's quite acidic. And there we go. Thanks for watching. That's our week 1 and 2 videos. I just didn't get around to doing them until week 10, but I hope that helps you with whatever you need help with. And yeah, always follow the units. Okay, bye.